First was the animal problem, which is the enumeration of clusters of a given size, and we showed that if you take this problem for directed animals, it becomes equivalent to a one-dimensional lower problem of just counting the different ways you can put nearest neighbor exclusion gas particles, particles with lattice gas but with nearest neighbor exclusion. So this problem, also, there was also a mention which I didn't do, but I just referred you to a paper where you can also study the problem which is not undirected animals. And that can also be shown equivalent to a hardcore nearest neighbor exclusion lattice gas problem, but two-dimensional lower. Okay, so what I perhaps didn't mention last time is an important point, which is the following, that you can take all clusters so these are animals, and these are called animals, and these can be clusters with, they can have loops. But you can also have something called branched polymers, and these are animals without loops. So, that is an animal with loops, but if you disallow such stuff, then you can only have things which are called branched polymers. Like that. And the number of animals like this and number of branched polymers like this, of course, are different. This one is less than this. So let us call these will be called AS, and these are called BS. Then BS is less than or equal to AS for similar lattice, embed on the same lattice, these different kinds. But so it turns out that these will go like some lambda to the power s, s to the power something, and this will grow as lambda a to the power s, s to the power minus theta. B and A, and it turns out that theta B equal to theta A, but lambda B is not, lambda A is bigger than lambda B. So if you are interested in the critical exponents only, then these two problems are the same, but if you are interested in the actual numbers, then of course they are different. Okay. So what I would like to do today is to discuss a very sort of nice symmetry which is called duality in percolation theory. It is one of the oldest results in percolation theory, and it's still very interesting and nice. And more generally, sorry?
A, B, and these are number of clusters.
Yeah, A and B are number of clusters of size B, size S.
Why is it negative? It goes down or is
No, lambda is greater than 1, and S is, usually this theta can be, that is the notation. Theta can be negative, but it is half or 5 by 6 or whatever.
but it grow, right?
Yeah, because this is the leading term. Okay. This is only a power law correction. Okay, so there are several kinds of notions of duality, but one of the things which is often used is what is called strong coupling, weak coupling duality. If you have some theory in which some coupling constant is very big, then you can change variables and convert it into another problem in which the coupling constants are small, and vice versa. So that is called strong coupling, weak coupling duality. But we will actually use a different notion which is called graph duality. And somehow I guess it gets related to the other one, so we will not quibble too much about this detail. What we will end up doing is to show this duality, graph duality for percolation problems, says that bonds which are present in some sense are related to bonds which are not present. So if you think of the bond present as some kind of coupling and bond which are not present as some kind of weak coupling, absence of coupling, then even this looks like strong weak coupling duality. But I think it is useful to keep this distinction in mind. Right now what we are discussing is geometrical duality, and it is defined to begin with on planar graphs. So we will consider a planar graph. The bonds will be denoted by line segments. Then two dimensions may be, okay, so here is a picture. So I take, sorry, I think I have to go back. The two-dimensional space can be divided into disjoint polygonal areas called faces. The boundaries of polygons have vertices and edges. And so here I have taken this space, and you can see lots of polygons, red polygons. And the space is divided into these polygons. Okay? That is the starting point. I divide the space into polygons. But then I can draw these lines, and those lines have lines and edges and vertices. Okay, so there are these things, faces and edges and vertices. But now I want to interchange their roles. For each face, which is a polygon, I define magenta, light blue blob, blue vertex. Okay? So then there are all these vertices. If two faces, two polygons share a common edge, then I draw a line connecting them. Okay, so those are the blue lines. Okay, so then the same picture can be represented by a graph, which is the blue graph. Instead of the red graph, I have a blue graph. The faces of the previous graph become vertices of the next graph. For each face of each yellow polygon, there is a blue blob. Okay? And if the lines which are the red lines, red edges, are, yes sir. Which one? On the right side. This one to outside. Yeah. This is, you should think of this as a part of a much bigger structure. It is not the end of the system, it is just a part of the big system. There are lots of other things on the other sides. Yes, sir. Oh, this one. Okay, that's a mistake. Sorry, that is my mistake. Okay, I was just drawing it, I forgot to draw that. There should be a line connecting there as well. That is correct. Okay, so then, so this graph, the blue graph, is called the dual of the original graph. If the original graph is called G, the dual graph is written here as G tilde. And you can take the dual of the dual graph, because the dual graph is also planar, and that you will get back the original graph. Okay, because this dual graph polygon is this triangle, and in the middle of that is the face of that dual graph is the vertex of the original graph. So that's a duality, it's pretty straightforward. And so that's what it says, the dual of, this should be a capital G, not small g. Okay, so this notion, now my picture drawing capabilities become stretched a little bit, but you can do this in 3 dimensions, and you can do this in your head. So suppose I take some 3-dimensional space, I break it up into cells, 3-dimensional cells, okay, and then intersections of adjoining cells, if there are 2 cells which are touching each other, then there is a face, which is a polygon. And if you take 2 faces, then they might intersect on a line, they may have a common line. And if you take 2 lines, they may have a common vertex. Okay, so that is how you go down in dimension. So this we can do even in 4D. This is even harder to draw, but I can imagine. Okay, so we define the sets on vertices. So now I will take the vertices of this graph, this G, and call it n edges as G, and this will, the fact that we started with some 3-dimensional space which was broken up into what I call cells, which are sort of disjoint volumes. That's a basic notion, and that is the equivalent of what is called planar graph, with the graph which can be drawn in a plane. Here we are saying the cells can be drawn in 3-dimensional space. Okay? So in the dual graph, there is a vertex for each cell. So now I have these planar cells. In the center of each cell, I draw a vertex. And if 2 cells are adjacent, I draw an edge. So then they will share a common face. If 2 cells are adjacent, they will share a face. So each face of the original graph corresponds to an edge in the dual graph. And each edge of the original graph corresponds to a face, because there the picture becomes a bit harder, but this you can see. And so in the dual graph there is a vertex for each cell. We draw an edge if the volumes correspond to endpoints. A surface on G tilde corresponds to a bond in G, and each cell in G corresponds to a vertex, just like before. Whatever we did before in 2D, which was a very nice and simple picture, I can do in 3D, but the pictures are harder to draw. Okay? Okay, so now let me consider the percolation problem in 2D, but we will consider it on the square lattice. So let us start with percolation in the red problem. So there are the red sites, and there are bonds, red bonds, and they form some cluster. And the dual of the red are the blue bonds. Okay, and maybe this picture I should draw better. This is the red lattice, and some of these bonds are present. And other bonds are not present. Okay? So now what I do, there is a blue chalk as well. So now I draw the dual graph of this. In the dual graph, the vertices are these things. Okay. And I will draw a dual edge if the the edge like this is drawn if the original edge is not present. If there is no red edge joining that, then you draw a perpendicular blue edge. So that is what is done here. So then you see that the red clusters and blue clusters kind of interpenetrate and cross each other. But the blue problem is also a percolation problem. There is a blue lattice which is a square lattice, and some edges are present and some edges are not present. Right? When is a blue edge present? When the corresponding red edge is not present. That occurs independently with probability P. Okay? So the blue problem is also a percolation problem. It is on the dual graph. And so we say that the percolation problem is self-dual. The percolation problem on the square lattice, if you take the dual, it's also a percolation problem on the square lattice. If I didn't take a square lattice, I took some other lattice, then the dual lattice will not be, if I take the triangular lattice. The dual of these are these vertices. And you can check, they actually form what is called a honeycomb lattice. Okay, the red lattice is the dual lattice to the triangular lattice, the honeycomb lattice. So the percolation problem, bond percolation problem on the triangular lattice will correspond to the bond percolation problem on the hexagonal lattice. It's the dual of this problem will be that one. But on the square lattice, the dual is the same problem. Okay, so that has a very interesting consequence. So there is an obvious geometrical property. Either there is a connected path of red bonds from left to right, or there is a connected path of blue bonds from top to bottom. Okay, is this quite clear? Either there will be a connected red path from left to right, or there will be a blue path from top to bottom. The only way you cannot have a connected red path from left to right is if there is always a break. So there must be a blue path from top to bottom. Okay, so now I will use some heuristic, actually not heuristic, but the correct argument, but not rigorous in the mathematical sense. So I will say that, look, suppose for the percolation problem there is a PC. If P is bigger than PC, then there are a lot of paths. So we will say that if P is bigger than PC in the red problem, then there is a path from top to bottom there is a there is a red path from left to right. For large L, with probability 1. So if you take any finite graph, there is always some probability that there won't be any path from left to right, because I can just say all bonds are absent. That occurs with a non-zero probability, but that probability becomes very small if L is big. Okay? So one says that in fact the probability that there is a path sorry, it tends to 1 minus a very tiny number which can be made smaller and smaller if L is bigger. So I am taking this as a result. This I didn't establish, but I am taking it as an obvious result. I can prove it, but I will leave it as an exercise. Okay? So now, of course, there is nothing special about left to right. I can also write from top to bottom and also from top to bottom. Okay. So then it says that if P is bigger than PC, if P is bigger than PC red, then there is a red path from left to right. Okay, so there cannot be a blue path from top to bottom. So when the red bonds percolate, the blue bonds cannot percolate. Okay, it's pretty obvious and simple, so I'm not going to write infinite amount now. So there is a percolation threshold for the red bonds, and there is a percolation threshold for the blue bonds, and they have to be different. So I must have PC red is equal to 1 minus PC blue. If P is less than this, then this is bigger and this thing percolates, otherwise that one percolates. Okay? But the problem is the same, so PC red must be equal to PC blue. And so PC must be half. So this is a very famous result, The title of the paper by Kesten, where he proved this, was that PC for the square lattice is half. Okay, and it's very nice result, and it's obtained by symmetry. Of course, he, being a mathematician, proves it in much more effort, but then we will leave that, we will not do it. He does it so that, whatever I was sloppy about, the large L limit and stuff, he does more carefully. So he will work with L by L lattice and then take some result about, probability of percolation on finite L and then let L go to infinity. We have been sloppy, and we will just go ahead and assume that. So the result is that PC bond square lattice and this comes from the self-duality of the square lattice bond problem.
So this aspect is, the lattice remains square, but let us say that Lx and Ly is different, and the aspect, finite aspect is so.
Yeah.
Still it is half. Because
Yeah. So what happens on, so this result, which is still true, if L is large, even if there is a finite effect, if P is bigger than PC, then there is also a path from top to bottom and path from left to right with probability Y.
the aspect ratio is different. It is
Huh.
possible that there is a path from top to bottom, but
Yeah, so for large enough L, it is true. No. So there is a subtlety involved, is that if P is near PC, then the fact that, you are working on this graph or this graph, then the probability to go like this is different from the probability to go like this. Okay? All those effects are there, they can be worried about. But if I take the large L limit first, or keep it big enough, then I don't have to worry. Okay, so that is what that's the attitude I am taking now. Without writing the next equation, I have just orally said that PC bond on the hexagonal lattice must be 1 minus PC bond on the triangular lattice. Same duality. All the arguments are the same, but that one, since it relates to PC of hexagonal lattice to PC on the triangular lattice, I am not able to calculate explicitly either of them. Those values are also known, but then you need some extra argument to calculate them, and right now we are skipping it. And you can read it up, of course, they are available in standard sources. Okay. So this implies that for the square lattice bond problem, P star, which is the PC, is half. Okay. But now we want to study its duality on the site percolation, not bond percolation. Okay. So I take this hexagonal lattice and I have drawn the site percolation problem where each hexagon is, actually it is a triangular lattice. It's a triangular lattice. I have drawn the dual hexagons. I like to look at it like this, that I could have drawn the triangular lattice, but you should imagine the centers of the hexagons as the vertices of the triangles, and I'm doing on the triangular lattice. It's actually the dual of the, but let's not quibble about this. Okay, so on this lattice, you have either filled pink hexagons or white hexagons, and each occurs with probability half. Each occurs with probability P and 1 minus P. And again there is a percolation threshold. Above the threshold, there will be a connected path of pink hexagons from top to bottom and left to right, and below that there won't be one. And again, it's the same principle. Either there is a pink path from top to bottom or there is a white path from left to right. Okay? So we can get this result. PC of site percolation on triangular lattice is half. Because the problem is symmetrical. Left to right or top to bottom is the same thing, no? They should have similar result. I just rotate the lattice like this. Okay? Even that was a slightly cheating operation. You should recognize the cheating when it is being done. It is correct, but it is not rigorous because the triangular lattice does not have 90-degree rotational symmetry. Okay? But the argument I gave was actually correct, and one should justify it better. And if I were to give pompous statements, it will be that the rotational symmetry is restored near the critical point. In the triangular lattice, it is certainly there is no rotational symmetry, but near the critical point, there is a up, down and left, right symmetry. But that is a claim, and it is not an obvious result, and it is correct, but it should be justified, and I am not doing it. Okay? So you should be able to find more educated proof of these results in some other place. All the references were given in the first lecture. Yes?
I mean, by this line of argument, can one always say a lattice and its dual will be exactly half?
Okay, no, very good. So let us just continue on this. Unfortunately, I thought about this, but I was too lazy, or my picture drawing abilities are not very good. So let us imagine what happens in 3D. I want to do bond percolation in 3D. Okay? So bond percolation in 3D, I take a cubic lattice and put some bonds or not put some bonds. What is the dual lattice? At each face, at the center of each cube, small cube, you put in a point. So it's also a cubic lattice, not a problem. But now, if I put a bond or not a bond, that will be equivalent to putting a face or not a face. So the bond percolation problem on the cubic lattice becomes what is called a placket percolation problem. You have this cubic lattice, there are all these 2 by 2 squares which are called plackets, and they each randomly you put in a placket or not a placket, okay, with some concentration P. Then what happens? At low P, you will have just isolated plackets, and then they will form clusters. And sometimes the clusters will become bigger and bigger, and there might be a cluster which goes from top to bottom, infinite clusters. Okay? Okay, very good. I can imagine that much. But now suppose I work on the other end. I work at very high density of plackets, almost all plackets are in. Then I remove some plackets. Then there are these holes, non-placket bar, non-plackets. Then the non-plackets can percolate also if their concentration is big enough. Okay, but now there is a problem. The plackets can also percolate and non-plackets can also percolate. In 3D, you can have a percolating red cluster and blue cluster at the same time. There is a red cluster, but in between the red cluster there can be interpenetrating blue cluster. Okay? So in the placket percolation problem, there is actually two critical points. There is a critical point, I increase the concentration of plackets. There is a point where the initially the blue plackets percolate and the red plackets don't percolate. Then you go to a phase in which the red plackets percolate, there is a path from top to bottom, but the blue are also percolating. And when you go towards bigger red, at some point the blue stop percolating and only red are percolating. Very good. So that is sort of answering your question. In 2D, it's not possible. That's why the problem was, that was the main line of the argument, that if there is a connecting red path, there is no connecting blue path possible. In 3D it is possible, and so it doesn't work. And since we are at it, we can also work in 4 dimensions. So I have a 4-dimensional cubic lattice, and I consider placket percolation in 4D. Okay? Now the dual of plackets in 4D are also plackets, because the dual of volumes was points, so 4D volumes will become points. The surface of 4D volumes are 3D surfaces which become edges, and 2D plackets, the dual are also plackets. Okay? So the 4-dimensional placket percolation problem is self-dual in 4D. Okay? And the PC will be half. That problem is not discussed enormously because it somewhat not easy to imagine straight away, because 4D hard to imagine, but I don't know. There are people who imagine 26 dimensions, so 4 should not be too much.
So the critical values for 3D is known, like both the critical values?
Yeah. So I think to a good approximation in 3D, bond percolation there is a P1 which is around 0.35 and P2 which is around 0.65. So these are dual of each other. So P is like this, 0 and 1. Here this is there are 3 phases, first phase, second phase, third phase. 0.3 to 0.6 there is a second phase, and beyond 0.6 is the third phase. Okay? So in the placket problem, you can have a case where the plackets percolate or don't percolate. But I can ask a more complicated question, which is that, do the plaquettes form a holeless surface? I have all these plaquettes. Can I find a surface spanning the whole system which has no holes? If there is a surface which has no holes, then there is no dual red line which can go through. Okay? So that's the question. The question is there a plaquette cluster which is infinite? That's a simple question. Is there a holeless infinite surface of plaquettes? That's a different question, and it's a different threshold.
So
Oh.
it will have a half.
In 4D it is half, in 3D there is a whole range. In this whole range,
No, no, but if you define your clusters to be only the one which is holeless,
huh,
not the other one,
huh.
then the critical value of that, having that or not having that, has to be half. No?
If you restrict yourself to that 2D surface, and you are asking what is the percolation probabilities of on that surface. This surface is it's not plane surface, it's a jagged surface. I'm not immediately able to tell whether PC is half or not, because it's a funny surface. Okay? I don't think it needs to be half, but I cannot be sure just now. We can think about this. Homework exercise. Okay, so now we come to something else, which is duality transformation for planar resistor networks. I like these resistor networks because I studied them in the 12th grade, and so I think I understand them well. Okay, so you take a resistor network, planar networks are easier to draw, so we think of them first. And so there is a blue network drawn here, and there is a dual red network also drawn on the same picture. Okay, and now there is a well-known result which I suspect even some of you know, some of you. There is a duality of electrical circuits which is called the voltage current duality. How many of you are familiar with this? Nobody. Okay, very good. Then we will discuss it because it's very nice to understand. Okay. When I was preparing this lecture, I just wrote on the Google voltage current duality, and then it gave some references of class notes of various places, but they were usually what is called circuit theory, electrical circuit theory. So I guess if you are a BTech student in electrical engineering, you will definitely have heard of it, but maybe none of you are BTech students in electrical engineering. Okay, so okay, it's no problem. So let us take a network of resistors. You can draw any complicated set of resistors and connect them together. Right now we are just ensuring that the graph you draw should be planar. Okay, so take a planar graph like this, then I take some multimeter and put the plus node here and then minus wire here, and see how much current will flow through this network when I connect them like this. Input of current from here, output of current from here. All the resistors are given. This is a standard problem. If the network was very simple, series and parallel networks, or a combination of series and parallels, then you can do it very easily. So I did it here. these two resistances are connected in series, I can replace them by a single resistance. But in the rest of the network, I cannot use this simplification because there is no other, this part is also right now, it is can be reduced to a single resistor. But after that, what do I do? So the way it is done is to say that, let's say there is a potential at each vertex, V1, V2, V3, V4, V5, V6. Okay, so 6, V7, V8. There were 8 vertices, there are 8 potentials, V1 to V8, which are unknown. But given these potentials, you can calculate the current in each resistor, because this will be V1 minus V6 by R1. This will be V2 minus V6 divided by R2, and so on. Given the voltages, you can calculate each current. And then there is a constraint that the net current at this should be 0. So, you should write current at this should be equal to the current sum of these two. And write all those current equations. Then the equations are as many as the equation, they become coupled linear equations in the VIs. This is a little bit of a problem, is that if you increase all the VIs by the same amount, then the currents don't change, and so the voltages are only defined up to differences. So I can set one of these voltages to 0, whichever one I like. Okay, and then what I said is correct. Then the number of equations you get will be equal to the number of unknown parameters, and you solve for each of them. Okay, so the equation is written as sigma times V equal to I. Sigma is a current matrix, conductance matrix. Its entries are 0 or 1 by R in suitable places. V's are the it's a vector V1, V2, V8, and I is a vector which gives you the net current in at a vertex. So here you will say that the current in should be equal to I, which is the net current in, and for others it will be 0. So these are called, this is called the Kirchhoff's second law, I think. Current at each node should be 0, except at the nodes where you are feeding in current, right? I can also take care of that one by putting in current source. Well, let us not get into that unnecessary detail. So if you assign voltages to each vertex, then you can express current in terms of these voltage differences, and then use the current conservation law to write coupled equations for these V and then solve them. This is the way I will solve this problem. Okay? But there is actually another way to solve the same problem, which is, so here, okay, so actually there is also a set of Kirchhoff's laws which you have read, which is that if you take a loop and say, okay, the current in this is something and voltage difference across here is something and across here is something, and if you add up all the voltage differences, you should get 0, right? In my way of doing this problem, that was automatically ensured because I chose the variables Vi. Then when you go along a loop, the net sum will be 0. So I chose the variables. I didn't write current and voltage for everything, Vi and I, too many variables. I only chose the voltages as independent variables. Current was written in terms of them. Then these currents satisfy some constraints, which are the conservation of current, and those were the equations which determine the V. I can do the reverse. I can start with currents as the basic variables. Okay? So currents as basic variables, I take the same network, So I will say that I am feeding in current I from here, but when I feed this in, it breaks into two parts. There is one current I1 and I minus I1 in the second one. So we will say that there are loop currents. I1, I2, I3. Okay? The current in this thing is the sum of all the loop currents. So it will be from here to here the current will be I2 minus I3. Is this, I suspect this is familiar to you, but I am still trying to ensure. It is familiar to everybody. So you write the all the currents in elements as the linear sum of loop currents. Then I will say that, then the first law, which is that if you take voltage difference from here to here plus voltage difference from here to here plus voltage difference from here to here, that should be 0, is a non-trivial equation in the current variables. Right? So you write down that law, and then the corresponding stuff for other. Okay? So when I choose the current variables as the basic variables, then the current conservation becomes automatic and trivial. Those equations are always satisfied. But the voltage equations become non-trivial. Okay? And I can solve it like that. Okay? So that's not a problem. But the interesting point is that on this graph, if you take the original graph and you solve the voltage equations on the graph, that becomes like solving the current equations on the dual graph and vice versa. It's not very profound observation. You can just look at the graph for 2 minutes and realize that this is true. Okay? So bottom line is that for planar resistor networks, there is a duality transformation. You can choose either the current variables as the basic variables and voltage variables as the derived variables, and then write equations for currents. Or you can write voltages as the primary variables and then write equations between them using the current conservation laws. This one, if you do on the, suppose I take the voltage technique on the first graph and write the equations, that will be the same equations you will get using the current techniques on the second graph, dual graph. Okay, so that is called the, and in the end you should get the same answer for the network, whichever way you use. Okay, so the, yeah, so it is, it just said here, briefly, let me read it once. This is used solving Kirchhoff's laws. One assigns a voltage variable to each node, determine the current in terms of, current in each link in terms of voltage differences, impose a condition that the net current is at each non-source node is 0 to get linear equations for V. Okay, alternatively define current loop variable psi j, and then individual current differences are, so individual link currents are differences of size, and current conservation law is automatically satisfied. But then one gets linear equations for psi I requiring that net voltage drop across a loop on the lattice is 0. Okay? So it is easily seen that the equations you get for psi I, these are the loop currents, but psi I will be in the dual lattice, they are the vertices. So in the dual problem, psi I are actually the voltage variables. And so the equations become the same if I assign to the dual variable conductance equal to 1 upon sigma of the other link, then the two equations become identical. Okay, so that is the resistor network problem on the planar graph, sorry, wrong spelling, is self-dual, but the conductance on the dual link is 1 by sigma of the conductance on the original link. Okay? So directed percolation. So it's interesting, this duality was known for a long time, like Kirchhoff was around 1850 or some such thing. So at that time, people had studied a lot these resistor networks and properties of them, and they derived some connections, and this in particular, the fact that they are related to linear equations and so on was studied quite a lot, and all these things were realized at that time. Okay, but this problem, the resistor percolation can be extended further to the case where the elements are not just resistors, but resistors and diodes. Diodes are one-way resistors. They allow current one way and not the other way. Okay? And so that is what we want to show, that this duality result can be extended to the case where the bonds have some preferred direction. And but we want to introduce these ideas. I think we already introduced the word directed percolation in lecture 1. But if a fluid flows along bonds is only possible in pre-specified directions, that affects the qualitative behavior of the problem strongly, and it is strongly continues to be studied a lot. And the point is that directed percolation clusters are very different from undirected percolation clusters. Their general behavior is different. And here is some picture of percolation clusters. You start the fluid at the top and let it percolate. For small p, it goes up to some distance and stops. For large p, it goes much further. So these are the clusters of percolation, but starting with the fluid source at all points on the top are wet. Okay. Okay. So if you think of the preferred direction as time, then the same picture can be thought of as the time evolution of a one-dimensional system. This idea also we introduced yesterday. You can think of it as a two-dimensional percolation problem or animal problem, or as a one-dimensional system evolving in time. And so then these things become prototypical examples for the study of non-equilibrium steady states. And I think so these problems have been studied a lot. But unfortunately, even the 1 plus 1 dimensional problem cannot be solved exactly. So, the directed percolation problem with one space dimension plus time, nobody has been managed to solve any version, any particular lattice, whatever you like of this, and it remains an open and interesting problem. So one can think of the infection of an orchard evolving in time, where the tree recovers after 1 unit of time. At low rates of infection, the infection dies out. Suppose you have an orchard and there are trees which get infected, but they recover. But if they are infected, they can infect a neighbor with some probability. But this probability is low. Then what happens is that typically one tree gets infected, but it recovers. And nothing, after it recovers, then the infection cannot spread because everybody is healthy. But once in a while, it may happen that the infected tree infects one neighbor, but then that one recovers and this one also recovers, and then, in the end, everybody recovers and the infection dies. Okay? But if the infection rate is high, then by the time this person has recovered, he has infected large number of other people. And the infection continues in the population even though the individuals keep on recovering. So this thing is called active absorbing state transition. So when everybody recovers and the infection dies, that is called absorbing state, because once you are there, you cannot come out of it. An active state is where there are some people who are being infected and infecting others and so on. And the active state can go on forever, sometimes for some ranges of parameters, and it will disappear for some other range of parameters. And this transition is called the active state to absorbing state phase transition. and this should be called generally. As you can see, the I didn't get enough time to read my own writing 2 or 3 times. And if you read it once, you don't detect all the errors. You have to read it 3 or 4 times, and I didn't manage to do it. So anyway, so for the absorbing state transition, there is a Jensen-Greisberger conjecture, which is very important in this field, which says that if you have a unique absorbing state and no special symmetries, then the transition is in the directed percolation universality class. Okay? And this has been studied a lot. It would be nice if one could prove it, but it has not been proved, and it is called a conjecture. Though nobody really believes that it will be found to be incorrect. If it's incorrect, then you just have to modify the statement of the conjecture to include the special cases where it is not correct. Okay, like it's right now it says if there are no special symmetries. This I will have to add if there are no special symmetries or one extra condition. Then it will continue to be correct. But it will be nice to know if there are any extra conditions needed or not. And right now the conjecture is exactly that. There are no extra other conditions needed to ensure that it is in the directed percolation universality class. Okay, yes.
Can you give some couple of examples where of systems where it falls into this
It falls out of this or in this? This.
of course,
So here this is this is an infection process where P is less than Pc. Bonds are directed downward with probability P and not present with probability 1 minus P. Then if P is small enough, then there are no clusters which go up to bottom. And if P is bigger, then they go up to bottom, and this is sort of the infinite cluster. Sometimes it has almost all the sites are in the infinite cluster. Okay. So I think I was becoming lazy, but I think the reason was that there was a limited amount of time and I have to make a selection as to what parts to include and what parts not to include. So I decided not to include too much about the structure of directed percolation clusters, the scaling theory of directed percolation clusters, which there is an analog of the scaling theory for undirected clusters, which also I didn't discuss here. Okay? So, there will be always some things which are left out, and I don't think one needs to apologize for that point. Okay. So there are two correlation lengths, C parallel and C perpendicular, that diverge with different exponents. Epsilon is the distance from PC. If epsilon goes to 0, this diverges, but it diverges as a power, and the powers are different for these two different correlation lengths. And equivalently, in the space-time picture, one is called the correlation length in space, and one is called the correlation length in time, which is called the relaxation time. Okay, so you say the correlation length diverges as this power, and relaxation time diverges as some other power. Okay. So now we want to actually get back to duality transformations for directed percolation. So what we'll imagine is for right now a square lattice. Each bond can be either what we call an insulator, means it doesn't allow any current to flow, or it can be a resistor which allows a current to flow both ways, left and right, or it can be a diode which allows current to flow left or to flow right, but only one way, and each diode is fixed, you know which way it allows. Okay. Now given this, so we will call them R is a resistor, I is an insulator, D plus allows the current to flow in the plus direction, D minus allows the flow in the diode with the negative direction. Okay, and in the x and y axis, in the plus direction, of course, is the direction of increasing y coordinate or x coordinate. Okay, now the dual bonds are assigned as follows. If the original problem, red bond, is not present, then the green bond is said to be an insulator. okay? And if it is forward biased, then the green will be forward biased. And if it is absent, then if the red bond is present, then the green bond is absent. Red goes to I goes to S, and D plus goes to D plus and D minus goes to D minus in the dual case. Okay, so this part is, I think, easily said. The red sides are the original lattice sides, green sides are the dual sides. I denotes an absent bond, R is the undirected bond allowing two-way flow. We have said all this. Okay. So if only R and I states are allowed, that was the original problem, percolation problem with two ways. Then we said that this problem is the old undirected problem. Now, in this problem, in the new one, we will say that these four types occur independently at each site with probability P1, P2, P3, P4. They all add up to 1, of course. Okay? So now I have a much richer problem with lots of diodes and resistors, and what happens in this system. Okay? Now several possibilities occur. One is that there are too many insulators, so there are a few conductors here and there, left or right, whichever way, but there is no net current possible. So the final phase can be insulating if it allows no current in any direction, or it can be conducting, in which case it allows current in all directions, positive Y, negative Y, positive X, negative X. Or maybe it allows current only in the plus X direction, but not in the minus X direction. And some other combinations thereof you can imagine. Right now we have not put in lattice anisotropy. So these probabilities P1, P2, P3, P4 are not dependent on whether the bond is an X bond or Y bond. Right? But I can also include them if I want, and they'll become even more complicated 8-parameter problem. So let us not do that, let us keep the problem 4-parameter. And so you can ask what are the phases possible in this general problem. So the dual of DI problem is a DR problem. So let us start with this sentence. So I start with the problem which is diode insulator network. So the bonds are either diodes or they are insulators. Either this bond is present or not present. If it is present, it allows current in. So that was the directed percolation problem we already studied and understood. Okay. What is DR? So now I take this problem in which some bonds are present, but others. Then in the dual problem, the diodes become diodes, and the resistors becomes insulators. So I have a problem in which there are only diodes and insulators. Okay? All right. So this is my problem now. Sorry, diodes and resistors. DR percolation. Diode resistor. So let's take a simple case where all the bonds are diodes. So they are all bonds allow flow like this. If I start with a source here, this can flow in all these sites will be reachable by the source here, and all the other sites will not be reachable. Okay. Now suppose I add a few resistors in this, 1% at random. If I add the resistor here, it doesn't matter because anyway the thing was able to reach there. But suppose I add a resistor here, then this current will be able to flow down here, and then using the diodes it will flow that way. You can always go to the right, whether it is a diode or resistor. Okay, but you cannot always go to the left. So this will be wetted, but maybe you cannot go here. But if you keep on going here, at some point there might be another resistor downward. Then you go along that and everything will be wetted. And anyway, if a site is wet, then it wets everything in the forward quadrant. So the statement is that if you look at the wetted cluster formed by a single point source, it will have a staircase structure. There will be some set of, there will be a line like this, such that things on one side are wet and the things on the other side are dry. Sorry? Yeah, in this side, this horizontal is not allowed. If you can go left only if it's a resistor. So I went like this, but there was a resistor, so I could go left and then go. And again, this should be a resistor, then only you can go left, and so on. Okay?
But the spread will be based on what we choose.
So the shape of this cluster is non-trivial. It will depend on the value of P. If P is 0, then of course it is this shape. P is no diode, no resistors are present, then it's like this. If a few resistors are present, the shape becomes sort of a little bit below is possible, and so on. Okay, but at least I'm sort of finding this much simpler than the problem of even diode percolation. The point is that here the shape of clusters is much simpler, just a staircase, much simpler than the complicated branch structures possible in the diode insulator problem. Okay? So one can try to study what happens in this problem.
Is the limit shape known?
Sorry?
Is the limit shape known?
Yeah. So the limit shape of this is guessed. Let us say I'm only guessing just now that in general there will be fluctuations. There might be resistors possible which let you go even here, but in the end the shape is a staircase. The staircase has an asymptotic slope. Okay? So the shape is like a wedge, and there is a wedge angle, theta. And of course in this direction, theta is like this. So this wedge angle will increase as theta increases. So I will plot. Theta is sort of the asymptotic property as a function of P, starts out as 0 and increases. At some point, theta can become pi by 4, in which case this thing will become like this. Then if theta increases just a bit further, it will become like this. Okay? But if it becomes like this, then from this side, I can again use the same argument and say that all this will become a wedge like that. And it's easy to see that actually as soon as theta crosses pi by 4, it will wet everything. Is this argument clear? It's actually quite straightforward, but I'm just trying to ensure that you have understood. Initially, there is a, this, in the continuum there is some source like this, it wets in an angle. But once the angle becomes pi by 4, then the wetted cluster becomes like this. But if the thing becomes like this, then this sites will always be able to wet, from parallel like this, and then the whole thing will become wet. So in this problem, theta has a jump at PC. Okay, and what is this PC? This PC is just the by the duality. If the original problem was critical, then the dual problem will be critical. So the PC of DR, we called it DRP, it is diode resistor percolation, is equal to 1 minus PC DIP, diode insulator percolation, which was just PC directed.
You can never wet the third quadrant.
No, no, no. Once you wet everything, then no. Third quadrant, for example, if this site is resistor, this site is resistor, you can wet up to some distance. But if
Diode only puts to the left.
no resistors, there are also resistors with finite concentration. Suppose everything is a resistor, then of course you can go to 3. Suppose there is 99% resistors, then also you can wet fully in the third quadrant.
So the cluster is always single cluster.
The cluster is a single cluster. Actually, that is by definition. The cluster is all the sites which are wetted by a single source. So it's a single cluster. No, sorry. If you make the source point different, then the cluster will be different. Sorry.
But every source will wet all the
Sites on the cluster. Right. So the wetted cluster cannot have holes. The point is all the holes will be filled by the wetted sites on the left or below. So these things are very robust and very simple to see. And so this problem becomes a bit easier to understand than the other one. So this is what it says here. We consider a source at the origin and look at the region that can be reached by the fluid. It is easy to see that the flow in the negative direction is So, sorry, when I wrote this, then my conventions for writing were different. Right now, when I was speaking, all the diodes were forward biased. They allowed things to flow in the positive direction. When I was writing this, I allowed them to flow in the negative direction. So there is a confusion of notation. But anyway, the point is that a site which it is wet, then it wets everything in the forward quadrant in this notation. And hence the wetted cluster is like a single staircase. On a large scale, it forms an approximate wedge. And initially the wedge angle is 90 degrees and it slowly increases. Once it crosses 180 degrees, then there is an instability and the angle jumps to 360 immediately. Okay. And so this was a picture I drew. So here the diodes allow leftward and downward flow only in this picture. Okay, and the resistors are only the red bonds which allow two-way flow. So when I started here, I could go up to here, but because of these resistors, I could go to the left, and these resistors let me go to the left, and the wetted cluster is everything which is below the dark blue line. Okay, just to, okay. For the general case where you have insulators, positive diodes, negative diodes and resistors, the system has 4 possible phases: no flow to long distances, flow in positive direction, flow in negative direction, or flow in both directions. Okay? And the phase diagram can be drawn in a tetrahedron. PQ, P plus, P minus, and this is notation taken from an article by Redner, and so I follow. This notation is different from the one I used here. But anyway, if you have 4 numbers which add up to 1, they can be denoted by points inside a tetrahedron, and each point denotes a particular value of P1, P2, P3, P4 in my notation, with the sum being equal to 1. And then this is the then there is a symmetry in this tetrahedron. If P changes to Q, that is the resistor and insulators are flipped, you get the same problem. Right? If there is a connection through the duality. The properties of the system when there are too many resistors can be related to the properties of the system when there are too many insulators by duality. Okay? And of course, P plus and P minus can be exchanged, because you can just define plus direction as the negative direction in the new convention. And so this tetrahedron has 2 symmetry planes, and so that constrains the behavior. But exactly what does it do? that you can figure out. I mean, it is not such a big problem. It is quite easy to figure out for yourself. If you fail to do it on your own, then you can look up this paper by Redner, but I would recommend that you don't do it first. Try to figure it out, what can you say about this simple problem by yourself first. If you are not able to think at all, then you can try to read the paper. Even if you read the paper, you read the first 3 pages and they say, okay, now I can figure it out myself and do it. If you cannot do it even then okay, read one more page, like that. Okay. So exercises. Sorry? What is the question? Where are the phases? These are just the symmetry planes. I didn't draw the phases. Which region? Qualitatively, can you tell which region allows no flow? This one I'm helping you along in getting the answer. I'm saying this much I can answer. If, no, I'm giving the answer here. Suppose Q is, the point is near this here, like there are too many insulators. Then, even if you put 1% of anything else, it will still not conduct. So, region around here, sorry, it has stopped. There is no more, anyway, region around the left corner will be all insulating, no flow. Similarly, region around right will be all conducting, because there are too many resistors, a few holes doesn't matter. So, one on the left it is insulating, on the right it is fully conducting, on the top it is only flow in the positive direction, on the bottom it is only flow in the negative direction, and then these boundaries have to join in some funny way that you have to figure out. Okay. Sorry? So that is for you to think about. This problem has not been solved fully. Only some symmetry properties are known, but the full solution is not known. In particular, there are some multi-critical points where different phases come together, and those are also not understood well.
P is concentration of resistors, right?
Yeah. In that picture, P is the concentration of resistors.
No, so this one.
Yeah.
You wait that this third quadrant. Is the P greater than PC? Is this half or?
No. This is the directed PC. Usually.
No, this problem.
Here.
Yeah. It's still half or less?
No. It is 0.3 or some such number. It's 1 minus P directed.
For the third quadrant.
Yeah.
So it reduces because of the.
Yeah. Because of the, it's a resistor, so a lot of things allow two-way flow. Then even 0.3% of resistors is enough. Anyway, all the diodes are present.
Yeah, but in the third one, the resistors are.
No. So the problem is not immediately obvious, but it is actually easier to think about than the original DIP. And to that degree, it is useful. And so the exercise here is actually only this one. This is very simple. You have this small graph, and I put current between A and C. 1 volt difference between A and C. All the resistors are 1 ohm resistors. How much current will flow? Okay. The point about this problem is, don't say that, oh yeah, there are some equations which you can solve, and leave it at that. You should actually write down the equations and solve it. Okay. Better still, can you get the solution without writing down all the equations? So Professor Feynman used to say, can you get the solution in the shower? You are given the problem, you don't have pencil and paper, and you should still be able to figure out what is the solution. That's a good exercise. For very complicated problems, you cannot do it. But for some problems, you should be able to exercise your brain to be able to do it. So this is the one which you should be able to solve in the shower. Okay, so that is the exercise.
Two.
Hmm?
Two ohm answer.
I still didn't follow.
2 ohm answer.
2. No, 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 2 is incorrect. Why did you say 2? Two is incorrect. Okay, so we can stop here, or we can use this opportunity to let you ask some questions about the previous material we covered. Yes.
So here you have initially taken all our diodes.
Yeah.
And then you are putting some resistors with some probability T.
Yeah.
And as per I have understood, you are measuring how much fraction are conducting currents and
Yeah.
and that is the.
I was finding out what are the set of sites which are weighted by a point source at the origin.
But if you take in other way,
Hmm.
that if initially all are resistors,
Hmm.
then all the sites are conducting current.
Hmm.
If you put the diode with certain probability,
Hmm.
then can we define some percolation threshold in that case also?
Precisely. So that's what I did. So okay, let us imagine that there is a network in which all the bonds are square lattice, all the bonds are resistors. Then I put a point source at the origin and I ask what sides can be wetted or reached by the fluid, which can, the resistors allow two-way flow. The answer is the whole plane, right? There is no problem. Now suppose I make some of the bonds to be insulators. Okay, then we also know the answer. Initially, most of the sites are still reachable, but there might be a few sites. This site, where this is also an they is not connected to anything. All these bonds are present, but these 4 bonds are actually absent. Then this site cannot be reached. So the infinite cluster, the set of sites which can be reached by the source at the origin, will contain many sites, but may contain some holes. The holes can be of size 1 or 2 or more. Okay? But what is the probability that there will be a hole of this size? It is q to the power 4, with 0.1 probability of bonds being absent. The probability is 0.0001, very small. Most of the sites will still be reached, right? So the cluster will be still two-way percolating, even though you have put in a few diodes and insulators, right? But now I am saying, suppose I consider some other limit, everything is a diode. Then you can only flow in some directions and not in others. Then if I take a diode and make it into a resistor, then the size of the weighted cluster can only increase. Okay? So using these kinds of arguments, you should be able to figure out exactly what is the region or qualitative shape of the region which allows for two-way flow, one-way flow, no flow, right? Like that. In that paper of Redner, actually they prove something more than what I discussed here. They say that if you have a conducting element allows two conductances, sigma forward, sigma backward, which are not equal but don't have to be 0 or non-zero. So it can be 0.3 and 0.1. So it's kind of a diode, but it allows more easily current flow in one direction, but allows current in the other direction. So for such networks also there will be a net conductance of a big sample. What is it? And it turns out that for this more general problem with various choices of sigma f and sigma b, there is still a duality transformation where this bond is given to a sigma f prime is equal to 1 upon sigma f, sigma b prime is equal to 1 upon sigma b. This is the dual bonds, you just allow them with 1 by sigma of the old one, and this is a generalization of the duality transformation we discussed so far. And these values, sigma f, sigma b, can be different at different bonds. All you need for duality is that sigma goes to 1 by sigma, and the network properties are preserved. Okay, so I think we will stop here.
So the boundary of this cluster DRP
Yeah,
is like a random walk, just kind of moving either forward or down.
yeah, it is. It is a random walk, but it is a correlated walk. It is not a.
Wedge angle, and then one can find the wedge angle and figure out what exactly, where exactly the wedge angle becomes.
Yeah. So that would determine PC. If you could determine the wedge angle. The wedge angle for this problem is actually, suppose you take this diode insulator percolation. Then there is a wedge angle of the weighted cluster. So for P bigger than PC, there is a theta of P which has some dependence. Below that it cannot wait, above that it waits. This wedge angle dependence is actually deducible from this of the dual problem. Okay. I think my idea is not to put in too much material in one lecture, because then it becomes hard to absorb. So I think this much, if you can understand, it's okay. And I have a few minutes, so I can only revise what is already done here. Okay, so let us just remind you. First point is that there is a duality on graphs. Planar graphs, you can make a dual graph. And problems on the graph can be related to problems on the dual graph, and they can be self-dual sometimes. And then it says that the bond percolation problem on the square lattice is self-dual, and that said that P star is half because of the symmetry property of this graph. And then we said that same general rule tells you that for the side percolation, triangular lattice will have a percolation probability half. Same argument, everything goes through. Either they can be a connected red path, or there is a connected blue path in the perpendicular direction, right? And then we just said that this duality transformation can be also generalized to resistors, not just percolation problem yes or no, but values of resistances. And the problem was that a resistor problem on the blue network can be converted into a resistor problem on the red network with suitable resistances along the red bonds. Okay. Sorry? So in the electric field, it's called voltage current network, but now I've forgotten that one. I only remember graph duality. So there is this graph, blue graph and red graph, and there is a resistance problem on the blue graph that can be converted into a resistance problem on the red graph. Okay? The resistance problem on the graph you can study using voltages or currents, whichever is your favorite. I don't care. Okay? And then this part was easy. And this was the duality transformations can be extended to the case where each bond takes two possible values, sigma forward, sigma backward. And then the dual network will have sigma forward prime, sigma backward prime, which are just 1 upon sigma forward, 1 upon sigma backward. And they can be any distribution, whichever way, and it always works. And that's an interesting result on its own. You can explain it to your younger brother who is in the 10th grade, right, without too much problem. Okay, and this is for to make you realize that there is actually some structure in the problem which is not figured out fully. So it takes some effort to actually come up with non-trivial results even for this, and many non-trivial results are not known. So whatever you cannot solve in 5 minutes usually takes very long time to solve. That is the definition of non-trivial. If you can figure out the answer within 5 minutes, then it is trivial. If you cannot figure out within 5 minutes, then it is non-trivial. And by some measured theory, most of the problems which are non-trivial are also very hard. The set of problems which are non-trivial but still solvable is very small. So you have to look for them and see if you can manage. Okay, we will stop here. Yes, sir. Sorry? Yeah, something like that, yeah. Can you explain it to everybody on the board? Maybe in the afternoon. You think about it. Maybe you got the answer right. Then you have to actually make it as simple as possible and explain it in the afternoon, in the tutorial session. Yeah, very good. Okay.
There for tutorial today.
Yeah.